Hello, everybody. I'm Alessandro. I should have been doing this talk with Prashanth, who works with me in the systems enablement team at Red Hat. He couldn't be here, so I will be taking the talk for him as well. What I will be talking about comes from the result of the works that we have been doing to build the Multiarch Tuning Operator in OpenShift. I'll stay in the intersection between scheduling, autoscaling, descheduling in Kubernetes, and I will be presenting, giving you some more historical context about the Kubernetes scheduling. I will present you what the scheduling Enqueue plugins are, and then I'll try to move forward in introducing this concept of two-level orchestration in Kubernetes, exposing challenges, and introducing Outrigger as the community where we are essentially exploring the problems related to these approaches. Let's start from the historical context. And well, let's start from what the Kubernetes scheduler is. It's a core component of the control plane in Kubernetes. Its main role is to essentially watch for pods that are not scheduled, find and compute what could be the best host, the best node to host that pod. And historically, the scheduler in Kubernetes is a very general purpose scheduler that was initially part of the Kubernetes repository code. It was, and it was essentially focused on configurability in terms of users being able to configure the policies that they wanted to apply in the scheduler. However, cluster administrators who manage Kubernetes clusters might need to rely on different strategies based on the scenarios that they are implementing in the clusters, and in the time, the scheduler evolved. Initially, the community introduced the scheduler extenders, which essentially allowed the scheduler to communicate with an HTTP service, an external HTTP service, to get informed about what constraints you want to apply to the placement of a pod in a cluster. This approach today is considered quite fragile. It's hard to integrate due to the versions queue. It also relies on asynchronous communication between a core component and an external service for which we might not have enough guarantees when managing the control planes. And that's why the community moved towards the scheduler framework that turned the scheduler into a pluggable system, a system for which developers willing to change the behavior of the scheduler could develop a custom scheduler out of extension points that are exposed by the API in the scheduler framework as an in-tree artifact. The scheduling framework's architecture looks like this. We can distinguish mainly two cycles: the scheduling cycle and the scheduling cycle and the binding cycle. In this presentation, I will not talk about the binding cycle, and we'll focus a bit more in the scheduling cycle and in the one that you see before that. Basically, pods are passed through a pipeline of different stages, some of which are extensible. A good way to distinguish between the stages is to discuss about filtering stages and scoring stages. With filtering, you essentially apply constraints that allow you to build a set of candidate nodes that you can where the pod that you want to schedule can actually be run. Once you have a set of candidate nodes, the pod passes through the scoring plugins. And what happens there is that each node is assigned a score so that the scheduler can decide to run the pod in the host that has the highest score. Now, we're talking about constraints and score, but what are we really talking about? What are these scores and what are these constraints? Imagine that you are building, that you are administering a cluster that uses an orchestrator that is not Kubernetes and it does not provide a scheduler. It provides any of the facilities that you might need, networking, storage, whatever, but you have to decide every time you deploy a pod where this pod has to stay. How do you decide that? You might choose to host pods that use the same type of resources in different hosts so that you avoid the interference given by using the same, I don't know, for a CPU-intensive pod. For two CPU-intensive pods, you might avoid them to stay in the same node so that they can perform as best as they can. If you care about networking, you might decide to let pods that are depending on each other from a network perspective into the same availability zone or even in the same host. Or if you move this further, you might try to let the pods stay in nodes such that you minimize the probability of violating an SLO. And if you think about it, every time I've done one of these three examples, I've been talking about some value that has to either be maximized, minimized, and that's why the scheduling problem in Kubernetes relies on theoretical problems coming from the queuing theory or from operational research. And they are problems that we face every day in different industries. That's not a case that Kubernetes blending takes from the shipping boats metaphor to build every controller, to build every of the branding messages. Imagine you are trying to decide how to place containers in an infinite number of boats. What would you look for? You will look for the space. You will look for minimizing the unbalance of the weight. You will look for, I don't know, minimizing the amount of gas required to run the shipping. Same is for placing boxes into shelves. And that's why I'd say scheduling is a problem for which we let a pod be an n-dimensional shape to be placed into an n-dimensional box. The scheduler can be essentially doing all of these all these examples by configuring, I don't know, beam packing. In the beam packing case, you try to minimize the number of nodes. In the least allocated policy, you try to put pods into nodes that have not so much usage of resources, still somehow maximizing or minimizing some of these parameters of efficiency of the cluster. And well, all of these problems can be, or most of these problems can somehow be represented by this typical and classical operational research problem. It is named knapsack problem. This is very similar. You have a backpack, you're going for a hike, and you want to put items into this backpack such that the weight of the backpack is less than a given threshold, and you maximize some value. Let's say the probability of surviving during the hike. There is one more problem in Kubernetes. As I said, the pods come one by one through a pipeline. And the operational research problem that I've been presenting assumes that you know the items you're placing into these n-dimensional boxes. That problem is also well known to be NP complete, which means we cannot actually have a solution to the problem that is optimal. You run heuristics that returns a suboptimal solution. And when it comes to a queue-based scheduling approach, this is even worse. You cannot, the solution is essentially even more suboptimal. There are two more components that help reaching a better solution than that. You know, like the Tetris board that I've been presenting is the perfect game that you can achieve in Tetris. And if you think of pods being the objects in Tetris, and remember the name, you actually would like that, but you end up with this. And the schedulers and the cluster autoscalers are somehow meant to support a rebalancing of the cluster state and the placement of pods in your cluster. And this is what, getting back to the scheduling framework, all of the scoring plugins, all of the filtering plugins do. You essentially provide inputs to these heuristics in order to let the scheduler take a decision that is as close as possible to the manual scheduling done by the SRE in the scenario of an orchestrator without a scheduler. When you implement a custom scheduler, you end up in an architecture like this. You might run a single scheduler that replaces the default one, or you might run multiple parallel schedulers, and pods are assigned to one of those schedulers. There are two problems on this. The first problem is that they compete on the same pool of resources, the nodes. So if two schedulers try to implement two contrasting strategies, you might end up with nodes in a configuration that doesn't resemble any of them. Plus, if you are running a scenario that can be optimized by Volcano's network-aware strategy, and that scenario also overlaps with another scheduler's coordinators' capability about storage closeness. I'll just make a random example. And you want both of them. What should you do in that case? You should either decide compromise. I don't care about storage. I'll work with only the network-aware optimizations. You could merge the two schedulers. It can be very tricky, as in you have to produce a new binary that implements both strategies. Or what happens in the ecosystem is that once these cases arise, some of these custom schedulers implement strategies that are implemented also by others, leading to a redundant effort in the community for implementing strategies, even if they are slightly different in terms of optimizations algorithm or whatever. So just to recap and move forward. Scheduling containers in Kubernetes, scheduling pods in Kubernetes has deep theoretical roots in several fields, engineering fields. Custom schedulers via scheduling plugins are the de facto standard that we implement today. We can end up in a situation where we have to implement similar strategies in different schedulers. And something that is worth noting today, Kubernetes evolution is bringing us to let Kubernetes be the to-go platform for running batch workloads. AI, HPC And these workloads require more efforts in terms of research and development in scheduling, autoscaling, and so on. And that's why a few years ago, this Kubernetes enhancement proposal has been merged and implemented in order to provide a new way to not build a new scheduler, but rather find a way to hold pods before they enter the queue that the Kubernetes scheduler consumes for assigning them a node. The default Enqueue plugin essentially allows you to stop a pod from being scheduled until a list of scheduling gates, which is provided in the specification of the pod, is empty. If it's not empty, the pod stays there in pending status. And there are some fields that are mutable, for example, the node affinity. When this happens, and while the pod is pending, someone else, a controller, even a user, could remove the scheduling gate to unblock the pod and let it be scheduled. And there are already some examples of operators that do use this feature, one of which is the Multiarch Tuning Operator that I've been introducing. Another one is Enqueue. Taking the example of the Multiarch Tuning Operator for a second, and to try to clarify a bit more what I'm talking about, what we do in the Multiarch Tuning Operator is to ensure that pods are scheduled into nodes that run an architecture supported by the images of which that pod consists. We work in environments that are essentially multi-architecture compute nodes environment, so Kubernetes cluster where some workers are, for example, AMD 64 workers, other workers are ARM 64 workers. And yeah, what we do is essentially considering a user creating a pod or a controller, an higher level object controller, we intercept the creation of the pod and we add a scheduling gate. At that point, the scheduler is waiting for the removal of the scheduling gate, and in parallel, a reconciler for the pod computes what architectures are compatible with it, patches the node affinity of that pod, and removes the scheduling gate so that the scheduler can assign it to a node. If you think about it, we are slightly controlling the scheduling problem from an external controller. So are we back to extenders somehow? Well, yes, we are creating these dependencies between the scheduler and another controller, and also between a controller and an image registry, which is even worse sometimes. But we are doing that in a way more reliable way. We are doing that by the medium of the Kubernetes API. We are doing that not with asynchronous communication, but with an asynchronous one. The Kubernetes way, or better, today's Kubernetes way. Obviously, what we get is not a full scheduler, as you do with the scheduler plugins. But you can still find some scenarios that you can optimize without changing the Kubernetes scheduler, but by just augmenting what the informations that the pod specifications provide to the scheduler are. We do that without changing the scheduler rather than deploying separate binary or deployment object in the cluster. And, well, if from one side we are back to extenders, from another side, are we moving towards a two-level scheduling approach? And with the motivation of the batch workloads that I've given before, the first thought that comes to my mind is Mesos. Mesos is or was, it's uncertain how much it's maintained today, an orchestrator that targeted batch workloads since the beginning. And it provided a two-level scheduler, way more complex than the Kubernetes one. There is a global scheduler in Mesos that manages the resources and that has the responsibility of offering these resources to local schedulers. Local schedulers that are bound to different frameworks. So you might have a local scheduler for Hadoop, a local scheduler for Spark, a local scheduler for long-running services, and so on and so forth. The global scheduler just the role of ensuring fairness between what's done by the local schedulers. So we see in this as an opportunity, as the opportunity of overtaking on the limitations that I've been mentioning of the custom schedulers without removing obviously how they can still be useful. Remember that, as I said, the Kubernetes scheduler is general purpose by design. Controllers that could augment the specification do not configure as a scheduler, but they can support the scheduler in taking their decision. And this is what we are trying somehow to do in the Outrigger community. We take the name, again, from the nautical metaphor. We consider a big boat that is Kubernetes and some supports, which are the Outriggers that do support the orchestration. And they do support it in scheduling, but they also have to support that in terms of cluster autoscaling and the scheduling to let that eventual consistent sort of environment that we can reach when these components work in parallel and independently. So this is what we are currently working on in the Outrigger project. It wants to be an open framework and an open community that explores this problem, and that in particular wants to give engineers and researchers the tools to prototype, benchmark, and deploy smarter scheduling strategies that support scheduling in Kubernetes. Let's see, what are the challenges though? So as I said, there are two operators that I know about that are currently using scheduling gates, one of which is the Multiarch Tuning Operator, another is Enqueue. Enqueue is a Kubernetes native job queuing system. It's meant to support scheduling and some other facilities in Kubernetes in order to run batch workloads. It provides features like gang scheduling, quotas, and it does some use of scheduling gates. So in the case study that I've been working on, I used the multi-architecture compute nodes cluster as an heterogeneous cluster. One thing worth noting, we consider heterogeneous cluster whatever cluster has workers that do run nodes of different sizes, type, hardware, spatial hardware, and so on. In our case, it was easier to work on a multi-architecture compute nodes cluster, especially for the deals with the Multiarch Tuning Operator. So this cluster runs Enqueue and the Multiarch Tuning Operator. It also runs an autoscaler gRPC expander that allows the autoscaler to consider what's stored in the preferred affinities of the pod specifications, so that another configuration of the Multiarch Tuning Operator tries to let the cluster autoscaler provision more ARM64 nodes than AMD64 with a 2-to-1 ratio. Let's think about it as a way to save costs for your infrastructure. Enqueue and the Multiarch Tuning Operator run and control the same set of workloads. And well, the first scenario that I tried to run is essentially architecture-aware scheduling with the multi-arch tuning operator and topology-aware scheduling with queue. And in this case, scheduling works just fine, which means queue can provide the information to enable topology-aware scheduling, while then TO, the multi-arch tuning operator, can optimize the architecture placement. There is one problem, though. The queue also uses to reconcile and to work on higher level objects, for example, jobs. In such a case, it simulates what the pod template will look like at creation time, and well, it does its decisions just based on that. At that time, though, the multi-arch tuning operator hasn't yet provided the information about the architecture. So you end up in a situation where the cluster autoscalers feature that I was telling you about just cannot have the guarantees that we wanted to achieve. I made it worse, and I tried to implement architecture-aware scheduling and architecture-aware quotas. In queue, you can define resource flavors to partition the set of nodes that run your cluster into disjoint sets based on tains, tolerations, labels, and queue can basically assign each instance of a workload to one of the flavors based on the quota that is already available at that time. Well, in that case, with no changes to any of the operators, with no other modifications in the Kubernetes cluster in general, the result is very random. The result is depending on the fact that is depending on which controller runs first. If the MTO runs first, we have information about the architecture, the supported architectures. If queue runs first, you can assign a workload to a quota, to the ARM64 quota, although that pod in the future will not support, cannot be run on that architecture. By doing some changes and ensuring ordering in how scheduling gates are consumed, you can achieve both the features, though. Still, as I said, queue can work with higher level objects, and well, the queue's job integration is still a problem. It's still a problem because it works on the higher level object when the pod does not exist yet, and we will end up in a situation for which the pod supports only AMD, but queue assigns it to ARM, and then the multi-arch tuning operator wants to assign it to ARM, but it finds the node selector, and well, at that point, it doesn't change it anymore. So what are the challenges? Well, the contract in the CAP doesn't give any information on how to prioritize controllers that make use of scheduling gates. Queue uses scheduling gates, but also reconciles high-level objects, and there is no way to anticipate what the future pod will look like. And the same happens with the autoscalers. If you reconcile the high-level object before the pods are mutated, the autoscaler cannot handle the information added by other controllers later at pods creation time. So what we envision in the Outrigger community is that with the rising of batch workloads issues in Kubernetes, with the rising of bigger clusters and multi-clusters environments, there can be controllers that do perform small behavior changes to the scheduler by informing it through pod specifications that we already have in the Kubernetes API without doing all the changes that are required for creating a custom scheduler. And well, I think the observability, just to add one more thing, the observability ecosystem in the past few years has evolved drastically. And the amount of data that we have today about what happens in cluster is huge. And sometimes they are not well used, or better. Perhaps it's time that we consume them in a way that we can achieve things like network-aware optimization, or even better, carbon-aware optimization. It is a big problem today with how data centers are growing to support AI workloads. And well, yeah, what we think in the Outrigger community is that the Kubernetes scheduling evolution clears the path towards a two-level scheduling approach, a two-level orchestration approach. And that's basically what we are trying to discuss with the Kubernetes community, what we are trying to go to somehow design and implement as facilities to benchmark, to deploy, to build smarter scheduling strategies in the Kubernetes ecosystem, taking from experiences like Mesos one that have been quite strong in terms of orchestrating batch workloads in production systems. Thank you very much. If you have any questions. Again, I think that there is no real problem. Like, that's still the de facto standard. I'm not saying they shouldn't be used at all. All of this control, sorry. The question is, what's the main problem with running multiple schedulers in a cluster? So I don't think there is a big problem in doing that. I believe it's still the standard and the de facto standard way to implement a full scheduler. However, multiple custom schedulers running in the same cluster means partitioning the set of pods that you run in that cluster in these joint sets that have to be assigned each one to each custom scheduler. And also, running multiple schedulers means to let the schedulers compete with each other about the node resources under the hood. So if you want to optimize collocation to avoid interference when pods use the same resource type, and at the same time you want to implement another strategy that will get in very contrast with that, are you really guaranteeing that nodes are really configured that way? How do you, it's a 50-50, how do you prove it? Any other questions?
I have a follow-up question.
Go for it, Nicholas. Say it again, please.
If I want to start writing a custom scheduler, what is the most common architecture design that I need to be aware of in order to make my scheduler fit with the other schedulers in order to create a race condition or other problems?
So the question is, how can I start implementing a custom scheduler, right? Well, the scheduling framework that I've been talking about is the most important documentation that you should read about. And there is a repository in the Kubernetes SIGs organization that is scheduler plugins, if I remember correctly, that allows you essentially to fork from there and work to build your own binary with perhaps a custom strategy that you may want to implement. Thank you again.